Here, I'm going to show you with a very simple example how to run one-way ANOVA in SPSS, how to understand the output, and how to report the findings. We're going to start with the car model example we used in our class slides. Basically, we want to compare whether there are differences in the number of major repairs for 3 different car models. It's clear that we have the number of repairs as the dependent variable, and the independent variable is the car models, which has 3 different values. So when I enter the data into SPSS, first, in the variable view, I'm going to create 2 variables. One is the independent variable, the other is dependent variable. I label them and I change them to their appropriate level of measurement scales. And once you've done that, you can come here to enter your data. You can code your 3 car models into 1, 2, and 3. Then for each observation, you record your number of repairs in the past 5 years. Be clear that we have each column for 1 variable and each line for 1 observation. The null hypothesis we're going to test in here is mu1 equals mu2 equals mu3 because we only have 3 groups. And we're going to choose an alpha equals 0.05. And in order to test the null hypothesis, we run the one-way ANOVA because we only have 1 independent variable. We come here, analyze, compare means, and choose one-way ANOVA, and put your dependent variable into this place, dependent list, and your independent variable belongs to this place called factor. And I want you also to request descriptive statistics and the test of homogeneity variance. And next week we're going to talk about the post hoc test, and this is the place you go to obtain the post hoc test information. And we'll choose Tukey and S and K for now. And now you can run your test. And we get the output here. The descriptive table tells you how many valid observations you have in each of the groups. The groups, remember, is defined by your independent variables. And the mean of the dependent variable, the number of major repairs was in each group, and the standard deviation. And the second table we have here is the test of homogeneity variance. Remember that we have 3 underlying assumptions we need to meet in independent samples t-test and the ANOVA test. They are independence, normality, and homogeneity variance. The last one is the most important one. That's why we always test the homogeneity variance when we run ANOVA. And the assumption here is all 3 populations have equal variance in terms of the distribution of repairs. And with alpha equals 0.05, you want this p-value, the sig value 0.088, to be greater than alpha. In that case, we fail to reject the null hypothesis. That means we meet the assumption of homogeneity variance. If ANOVA is the show you want to watch, this test is a ticket to watch that show. This test is not the ANOVA test. It's just a ticket to enter into the theater to watch the ANOVA show. This Anova table is the place where we find the information and make a decision whether to reject or fail to reject the null hypothesis which is mu1 equals mu2 and mu3. But before we look at the p-value and jump into the conclusion, we're going to understand the information in this table. In this table, we have 3 lines: between groups, within groups, and total. Let's start with the first column. The first column have the sum squares for each line, and we are going to look at the sum square total, which is the measure of total variation in the dependent variable in this particular study. And this total variation is based on this mean, the mean of all 15 measures. This is called the grand mean. And with the grand mean, we can have a calculation that shows the total sum squares. So for each individual observation, we find out how far it is from the grand mean. That's called the deviation score. We square the deviation. We do this for each of the observations in the data set. We end up the calculation by sum all the squared differences. That's how we get the sum square total of 64. Now we have the sum square for within group. Sum square within is based on the assumption that all 3 groups have equal variances, and the variance within each group is a measure of population variance that is due to natural fluctuation within the population, random sampling error. So how do we get this number? We find out how far each individual score is from its own group mean, square this deviation score, and we do the same thing for other scores in the same group, and do the same thing for other groups. And at the end, we have a total of squared deviations within the groups, and this is the sum square within. Now the last one we have in this column, the one at the top, is the sum square between. Sum square between is another way to estimate the population variance. What we have here is 3 group means. You consider the 3 means as a random sample of 3 from the population, the same population, if the null hypothesis were true. Then you find out, okay, how far the group mean is from the grand mean. I square the deviation scores. Remember, we have 5 in each group, 5 observations in each group. That's why times 5. And this leads to a between group sum score of 40. Remember from descriptive statistics, sum square divided by degree freedom gave you the variance. Here we have sum squares divided by degree freedom. We have something called mean squares. Mean square is just a variance estimate. It's just called by a different term in the context of ANOVA. For between group, the degree freedom is the number of groups less 1, so it's 3 less 1. That's why we have 2 here. And for the within group, it's the group size less 1, and you do that for each group. You add them up at the end. So we have 5 in each group. 5 less 1 give you 4. 4 times 3 groups. That's why we have 12 for the within group degree freedom. The total degree freedom is the total sample size less 1. So we have 15 less 1 give you 14. Another thing you want to notice is that when you add up between group and within group sum square, you get the total sum square. So that's how we do the partition here. And same thing, when you add up the degree freedom between and the degree freedom within, you get the total degrees freedom. Now, we have 2 different ways to estimate the population variance. One is using the between group sum square divided by degree freedom. The other is using the within group sum score divided by its degrees of freedom. And the second one, the within group estimate of population variance, is unbiased. It's always unbiased estimate of the population variance. However, it's different for the between group estimate. This between group estimate of population variance is unbiased only when the null hypothesis were true. If the null hypothesis were false, which means there are significant differences in the population means, then this particular estimate of population variance have the population variance and also the treatment effect. And the F observed value we have here is simply the ratio of the mean square between over the mean square within. How likely for the F observed to happen if the null hypothesis were true, if there are no difference across the three populations? It's only 3 out of 1,000, 0.003. This means if we could repeat the same study for 1,000 times, only 3 times out of this 1,000 repetition, we can get a F value that's 10 or greater. So we compare this sig, the p-value, I always call this the p-value, with alpha. Since the p is lower than alpha, we're going to reject the null hypothesis. And the conclusion is that there are significant differences in the average number repairs of these three car models based on alpha equals 0.05. So we know there are some differences in these three means. The next question we need to answer is exactly which model is different from which model. So that's what we are going to do next week. We're going to do so-called the post hoc pairwise comparison. And the Tukey test is one of the choices we have, and here's the output. You can see that based on the Tukey test, you have model 1 versus model 2, model 1 versus model 3, and model 2 versus model 3. The other three pairs are redundant information. And we look at the column, the sig, the p-values, and compare them with your alpha equals 0.05. And this particular pair, model 1 versus model 3, has a p.002 lower than alpha. So model 1 and model 3 have significant differences in their average number repairs. And another pair is, just for example, we have another pair that is model 2 versus model 1, which has a p-value greater than alpha equals 0.05. Here, we conclude that the differences in the average number repairs between model 1 and model 2 is not statistically significant. And the same is found between model 2 and model 3. So for the pairs that do not have significant differences, we call them homogeneous subsets. So model 1 and model 2, they are homogeneous subset. Model 2 and model 3, they're homogeneous subset. However, if we look at a different way to test the pair differences, the pairwise differences, the SNK test found out there's no homogeneous subsets, which means all three pairs have significant difference. What are the difference between the two different ways of post hoc tests? We'll talk about the details next week.